A is a constant, as it is, it comes. Sin theta, when I differentiate, it becomes cos theta. So sin 2 pi ft will become cos 2 pi ft. It's not theta, it is in some other variable. So I have to differentiate. Look at this, that 2 pi f will come as the constant that will come outside. So A, as it is here, 2 pi f will come out, and sin 2 pi ft will become cos 2 pi ft. I think this is a simple mathematics differentiation. People will know it. Now, from velocity, I want to find out acceleration. One more time, you have to differentiate. As it is comes, one more 2 pi f will come. Already one 2 pi f is there. So 2 into 2, 4. Pi into pi, pi square. F into f, f square. Cos theta, when I differentiate, it becomes minus sin theta. And the minus sign I have not included here, just ignore. Okay, you can keep it. So it's again sin 2 pi ft comes. So I have displacement, I have acceleration. Now I want you to pay attention to the magnitude of these sinusoidal waves, whether it is sin theta or cos theta. Together I can just give a common name as sinusoidal wave. Okay, so forget about this sinusoidal part. Forget about it. Concentrate on only magnitude. Here the magnitude is A. Amplitude. Okay. Here it is 2 times amplitude times pi f. One thing is pi value is 3.14 into 2, 6.8. 6.8 times amplitude will be more. That's a constant term, and you look at the frequency. If you vary the frequency, it will linearly vary with respect to frequency. That you have to note. This is very important aspect of here there is a f term here, and that f term, as when you are measuring low frequency, the amplitude will be small. When you are measuring the high frequency, the amplitude will be amplified because the magnitude is a function of frequency. So even small amplitude, because it is getting multiplied, that will look big in velocity. The same idea, when you look here, it is not 2, it is 4 times amplitude pi square. It is not pi, it is pi square. 3.14 into 3.14 and f square. If I am measuring normal amplitude, that first gets multiplied by pi square, approximately, let's say 10, and this is 4, so it's about 40 times amplitude. It is not just 40 times amplitude. When you measure 1 hertz signal, it is 40 times. When it is 2 hertz signal, it is 2 into 2, 4 times. 40 into 2 times amplitude. 40 into 2 into 2, 4. When you measure 3 hertz signal, 3 square 9, so 40 into 9. When the frequency increases, you look at the amplitude, it is 9. When it is 4 hertz signal, it is 40 into 6. Multiplied. It is just 4 hertz. 5 hertz, 25 times. 10 hertz signal will be multiplied by 100 times. So that's only a small frequency, 100 hertz. We in the mechanical system, we go up to 10 kilohertz, 11 kilohertz and all. Imagine that square, and such a big value will be there for acceleration. Okay. So the point that I am driving home is the amplitude of the acceleration component is multiplied by its square of the frequency component. Square of the frequency component. So, just doubles. Okay. Now, when do I choose displacement? When do I choose velocity? When I'll go for acceleration. Look at this graph. This is displacement. The same signal velocity, the same signal acceleration. You see, here acceleration is very small. I mean, the high frequency signals are very small. Here, the high frequencies, the middle frequencies, here middle frequency is slightly bigger, but this is still reasonably bigger. Whereas you look at this, what is so small, not at all visible, is very big, very amplified, very good, big amplification. Okay. Whereas here there is no big change. There is no big change. It looks very similar to here. It's look. In fact, this peak is become a small peak here. Same signal. The signal's displacement, if I measure, my waveform will be like this. Velocity waveform will be like this. Acceleration waveform will be like this. Of course, this is not time domain signal. This is spectrum. That's a frequency domain signal. Okay. Now, what is the point that we have to learn? Sir, you are telling some low frequency, all that. Now you have to look at the application. Okay, you are going to measure the acceleration of earthquake or a slow moving machine. For example, in cement factory, you will see a kiln. Okay, a small velocity rotation will be there. 1 revolution per minute or something like that. One big cylinder, the cement factory. If you go to Madhukarai, you can see. Otherwise, you go to Madhukarai and see. A big cylinder will be rotating slowly. There also, because of rotation, there will be some frequency, but majority of the frequencies will be low frequency. You will be more interested in this area. Here, the peaks are highlighted well if I measure displacement. So whenever the operating speed is less, I'll go for measuring displacement. Suppose I come home, mother is using wet grinder for making idli mav. Okay, so roughly 1200 RPM, maybe slightly less, because there is a belt drive that reduces the speed. Let's say about 400, 500 RPM. The grinder is rotating. Then there, for those kind of medium speed applications, if I use velocity, this response is good for medium frequency range. So I will go for velocity. Whenever I have very high frequency application, for example, mixing in your, what is the RPM of mixing in your home roughly? Any idea? Sir, students பேச முடியுங்களா அங்க இருந்து?
Sir, it is possible, sir. Professor, sir. Professor
Yes, sir.
Elangan, sir, can you coordinate with the students, sir? Reno Thomas.
Anybody knows the RPM of mixie in your home? சட்னிலாம் அரைக்கிறோம் இல்லையா, அந்த மிக்சியோட RPM anybody? Without looking at Google.
The 15,000.
யாராவது இருக்கீங்களா?
Pavitra, can you respond?
All right, no issues. Roughly 12,000 RPM to 18,000 RPM, depending upon the make, there will be variation. But this is a very high speed machine that you can have in home is your mixie. I think that's the fastest rotating motor in your home. Whenever you use frequency signal, you are interested in high frequency content acceleration. Okay, not only mixie, even 1400 rpm, 1440 rpm motor, for centrifugal pump 1400 rpm. For all most of the measurements I use acceleration. Okay, if it is very low rpm, we have to use displacement. It's not very high, it's not very low, but it is in the middle. You can go for measuring velocity. That's the criteria for choosing the parameter while measuring the application vibration. If somebody says I am measuring vibration, that means they are talking very vague. They should tell whether they are measuring displacement of vibration, velocity of vibration, or acceleration. That's very important. Now, typical machinery and its signal. Suppose let's have one gearbox. Let's say it is a lathe, and there are a set of gears. I make measurement, and it looks something like this. And this is time versus amplitude. This is a time domain signal. Okay. Now I do FFT. FFT means fast Fourier transform. FFT. I will get frequency domain signal. That means x-axis is frequency, y-axis is amplitude. So whenever you have this kind of frequency versus amplitude, that you call it as a spectrum, and that's a frequency response. Okay. Now here certain things are not visible. Okay, simply some green color signal is there, whereas we'll remove all markings. Here it's like a green color, top bottom, it's like going up and down. Okay, fine. So what do I understand? I don't understand anything. Okay, whereas if I do FFT and convert it into frequency domain signal, you see there is a peak at A, there is another peak at B, there is another peak at C, D, E, and then signal goes like this. Now, each of these frequencies will be a particular characteristic frequency of this particular rotating component. Some of them may correspond to the bearings, some of them will correspond to these gears, though they are corresponding characteristic frequencies. Now, sir, what is the use of this, sir? Suppose, let's say this is a characteristic frequency of one particular bearing. It is supposed to be, its amplitude is supposed to be at certain level. If it goes beyond certain level, that means that particular component has failed, or there is a crack in that component. There's some fault occurred in that component. Because of that, the amplitude will increase. Okay. So earlier, people have done fault diagnosis using the frequency spectrum. Okay, it's not frequency spectrum, it is spectrum. Whenever we say spectrum, it is frequency versus amplitude, so it's just spectrum. Okay, so they just use spectrum and identify that, you know, here there is a increase in frequency amplitude at this particular frequency, and from that they infer that corresponding to that, A corresponds to this big gear. That means there is some problem in that particular gear. When all components are good, they know for sure new component, new gear, they will have this signature and corresponding spectrum. That is called base spectrum. Base, 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 original for reference. They'll take it and keep it. Over the period of time, due to usage and wear and tear, this spectrum will keep on growing up to certain level of height. It doesn't matter to us, but beyond that, it's not good for machining operation. So we will keep a threshold, and if the frequency component amplitude goes beyond a threshold value, we stop the machine, look at which machine is creating, crossing the maximum limit, change the component, and then run. That's how people used to do maintenance in the using vibration signal. Right. I think so far we just gave an overview of what is vibration, what to measure. There are three phases of vibration: displacement, velocity, acceleration. When to choose vibration displacement, when to choose vibration velocity, when to use vibration acceleration, and how to use vibration signal for a fault diagnosis using FFT in frequency domain. I told in brief. Any questions so far?
Dear student, can you put this question in test box?
No questions, huh?
Sir, you can proceed, sir. No problem, sir.
Okay, sir. So now, next is now we wanted to learn ultimately how to do fault diagnosis using vibration signal. Okay, that is the theme that we wanted to explore in the name of guest lectures. For that, the strong foundation is taking a good vibration signal using sensor. So you should know how to take vibration signal first. For that, what are the sensors used, and how to use that signal for acquiring the good vibration signal that you should know. I heard from Professor Nehru that he has already covered vibration measurement. So I will just rush through these sensors. Wherever you need more clarification, you can stop me and ask. I can very well explain. And I will dwell upon only the last sensor, which is piezoelectric accelerometer, and then a few considerations with that we will stop today. The first one is mechanical lever type elementary accelerometer, where of course the diagram is not to scale. This is a big room size turbine. This is a small instrument. Okay, the instrument is fixed so that the plunger moves left and right according to the horizontal, and that movement is enlarged by this lever principle, and the enlarged version of this movement is recorded graph sheet in the form of a graph. By analyzing the vibration signals, people make necessary analysis. This is very primitive, very old type of accelerometer, okay, mechanical type. And later on, people had acceleration level indicators. You know, mostly if you go to companies, they don't want to measure vibration, you know, so many meter per second square. They are not interested. They have some machine. When something goes wrong in the machine, vibration level increases. When vibration level increases beyond certain limit, they wanted to get an alert, because, you know, in a factory environment already it may be noisy. Already there will be a lot of vibration because of so many machineries in one roof. They wanted to get some extra alert in the form of a light, in the form of some sound, something like that, so that the attention may be drawn from the operator, so that he switches off the machine and does necessary maintenance activity. For that, the vibration level sensors are widely used. From the parts of the machinery, there is a cantilever beam and there is a screw. The cantilever beam is slightly stretched downward with the mass, and now the body moves up and down. That means it has vertical vibration. In that process, up to certain limit, the mass will keep touching this screw. Thus, the circuit is kept closed all the time. When the body vibrates faster beyond the threshold limit, the mass comes out of the contact and thus breaking the circuit, making the circuit. So there will be intermittent on and off that triggers the relay intermittently on and off, that triggers both light indication and audio indication. Speaker, through speaker you can give audio indication, through light you can give light indication, so that this can be used as vibration level indicator whenever the machine goes beyond certain level. This is very old type brittle member. Again, this is also level indicator, but mechanical type. You take a mass about. This is like your little finger size, whereas turbine is your room size. I have drawn this big, whereas turbine small. So definitely it is not to scale. This blue color diameter is only your little finger diameter. Mass is about 100 grams, whereas turbine is your room size, the room in which you are sitting, that size, that big. So imagine big green color turbine, the small part is just stuck onto it. Imagine that. When the machine is going through horizontal vibration, the mass also goes left and right. Up to certain limit, the brittle member will be able to take the load and hold the mass along with it. If it is a ductile material, that will bend slightly left side, right side, and adjust according to the vibration of the turbine. But purposely we take brittle member. Okay, what is the property of brittle member? Break if it is not able to take the load. Since this is a brittle member, the vibration of the turbine up to certain extent it will try to withstand. We have designed specifically the dimension and chosen the material of the brittle member such that if the vibration exceeds this particular level of vibration, it will break. Okay, so when turbine vibration exceeds certain limit, the mass breaks, and then the brittle member breaks and it falls. Okay, in the slide, the direction of acceleration is upward. It is not upward, it is sideways. This is seismic type accelerometer where you have spring mass damper arrangement. There is a spring, there is a mass, there is a damper, and all together forms a spring mass damper system. Here you have the vibrating body. The body now vibrates in the vertical direction. As it goes, the mass moves up and down, and connected to that is an LVDT lever, and the LVDT core also moves up and down. Proportionally, you will have an electrical signal that you can take it out. This kind of sensors, you call it as seismic accelerometers. This is a strain gauge type where you have a cantilever beam attached to a mass, and in the fixed end, you have two strain gauges, one on tensile side, one is on compressive side, measuring the change in resistances, and which can be converted into change in voltage, and from which you can measure the acceleration of the body. This is capacitance type. When the mass goes up and down during the motion, the distance between the capacitor plate changes. The capacitor is inversely proportional to the distance between the acceleration of the body. This is an inductance type. There is a coil, there is a magnet, and whenever the magnet goes up and down in a coil, an EMF is induced, and that is proportional to the amount of vibration. So the electrical signal is directly proportional to the vibration. You will be able to measure the vibration in inductance type. LVDT, and just you have a spring mass system, cantilever beam. As the body vibrates, the mass goes up and down. Proportionally, the cantilever beam goes up and down, and that up and down motion causes the LVDT core to move up and down, which produces electrical signal. You can measure vibration. And the last one, piezoelectric type accelerometer. Since all these sensors your professor has already talked, I have not elaborated, just rushed through that. Okay. For last 15 years or so, I have been using piezoelectric type accelerometer, very widely used accelerometer. The reason for that is found here. The reason is its dynamic range. It can measure from 5 kilohertz to 25 kilohertz of vibration signal. Very high vibration amplitude, no, very high frequency signal, it will be able to measure. Okay, this is piezoelectric type accelerometer. The piezoelectric principle, you may know, the piezoelectric material is presented here. You can go up to 315 degrees Celsius from application point of view. All these are all advantages of piezoelectric type accelerometer. This is the construction. Of course, a similar construction you might have found in other books. This is there in my book. Different variants, design variants are there, piezoelectric material. One is a shear force type. This is compression type. This is bending type. How you keep the material, depends upon the design variation. And piezoelectric material, piezoelectric sensors, how you mount on the particular machine depends upon, depends upon mounting technique. Your vibration measurement will get affected. Now, theoretically, any teacher will teach like this: take one particular sensor, talk blah 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 about working principle, advantage, disadvantage, operating specifications, all that they will tell, isn't it? Now, see, now you have come to a practical side. You wanted to choose one particular amplifier. You have LVDT type, you have seismic type, you have resistance type, you have inductance type, you have seismic, so many piezoelectric capacitance, so many type accelerometers are there. Now I wanted to measure acceleration from one particular machine. Which sensor I have to buy? The question is simple. Okay, so for that you should look at the price and what is the range of frequency the mechanical system will give. The biggest challenge in vibration measurement is, before even measuring once, what is the range of frequency that say a machine will give, we may not know. That's the biggest challenge. For example, you have a fan rotating at 1440 RPM above you, and I have to put an accelerometer and take vibration signals from the fan. What is the frequency of the maximum frequency of the that object? I should know first. Then only I can buy the sensor which is capable of measuring such high frequency vibrations. Suppose if I am not taking into consideration, simply go to the market, find one MEMS accelerometer which will measure only up to 3000 hertz and put and measure, I will get some signal, I will get, but that is not the right signal. Okay, that's where the difference of the good engineer and bad engineer. Okay, putting some sensor, measuring vibration, you will get some signal, but that is not the correct signal. You should know what is the frequency, maximum frequency of the signal that you are trying to get from the system. So what is the RPM? Convert it into frequency, rotational frequency, and keep that. Okay, assuming that there is no fault. If there is fault, then you should take the characteristic frequency equation of those faults, find out the characteristic fault frequencies, so that again, those frequency components also you should calculate and keep. Now, the frequency, the sensor that you will choose should be able to measure those frequencies. So that is how you should choose whether it is capacitance type or inductance type or this type or that type. Let's assume a case where you have only 2000 hertz you have to measure. Sir, MEMS sensor also is able to measure. Capacitance sensor is also able to measure. Seismic, all, strain gauge, piezoelectric, everything can measure, sir. Then how do I choose transducer? Whether it is available in my local place. Yes, Sunrise Electronics, Ukadam itself, it is available. Go ahead with that, buy. Sir, it is a MEMS sensor. I have to buy from online, but 2 days it will be available. Only 500 rupees. Cost is a big major concern. Second is cost. Third is availability. Then you choose the sensor if the technical specifications are met. In the technical specification point of view, the major point that you will be matching is find out the maximum frequency, and your sensor frequency the dynamic range of the sensor frequency should be capable of measuring that frequency. After meeting that technical qualification, then cost and availability, nearby availability, all that you check and buy. So that's how you choose your sensor. Now you have chosen a sensor and purchased a sensor. Now you want to mount it on the particular machine to take the vibration signal. What are the mounting techniques available? You have glue mounting, stud mounting, and magnetic mounting. What is meant by glue mounting? You just take a Fevikwik, apply 2 drop in the accelerometer, stick it onto 1 or 2 minutes time. After that, you connect the cable, connect the analog to digital converter, that means ADC, DAC card, and take signal in using laptop. Okay. What is meant by stud mounting? You find out the machine where you have to take the vibration signal, put a small hole, maybe 1 mm, 1.5 mm dia, and put your tapping machine, use tapping machine and make small threads. That's called tapping operation. Okay, you make small thread in and you also make a corresponding stud and fasten the stud onto the hole that you have made, threaded hole. Now a small portion of stud will be above the surface. On that you mount the sensor. In the sensor also there will be a hole with the thread. You tighten that and make a fastening and mount it. This kind of mounting is called stud mounting. What is magnetic mounting? The bottom portion of the sensor will have a small layer of magnet, so that any metallic object you wanted to take this vibration signal, you simply take close to that, it will get stuck. You want to keep, because most of the machineries is made up of either mild steel, cast iron, or that iron sheet only, isn't it? So you have a magnetic mounting, and this machine you want to measure vibration, you just go keep above that. Because of magnetic effect, it will get stuck. Take the signal, then remove the magnetic mounting, and each of this mounting has some advantages and disadvantages. Mounting, what is the advantage? Anytime you can fix it, whenever you don't want, you can remove it. What is the disadvantage? Because there is a sensor and there is an object in between, you apply a glue. That glue will act as a damping and suppress some amount of vibration. So actual machine vibration is not coming to the sensor fully. For certain applications, but in most other applications it will be suitable. What is stud mounting? Because you are making thread and tightly fastening the sensor onto the object, no vibration signal will be lost, no damping, pakka signal will come in stud mounting. But just because you want to take vibration signal, you have to make a flat surface, you have to make a hole, you have to make a stud, you threaded a hole, my God, that tapping hole you have to make, all that damages the actual machinery to a small extent. So time consuming, and immediately you cannot remove it. Stud mounting, okay, all these are all advantages and disadvantages of stud mounting. How about magnetic mounting? Whenever I have some 10-15 machines, I want to take vibration signals, and all has this metallic part where magnet is able to get attached to, and I'll be preferring magnetic mounting because I can keep the sensor, take the signal, and come. What is the disadvantage? Whenever I have a vertical surface like this and keep the sensor, due to vibration, this may come down. And while going, it will go. While coming, the body will come, but sensor will not come. But due to magnetic effect, later it will communicate. There will be some missing of vibration. The sensor will come down during the measurement. All these are some of the advantages and disadvantages of magnetic mounting. So for my experimental studies, for most of the studies, I have used glue mounting. Whereas stud mounting, in very rare occasion, I have used magnetic mounting. I have seen, but not used for my own studies. Okay, so depending upon the application where you use, you can choose what type of mounting. These are all typical characteristics of piezoelectric accelerometer, and can go like that. Okay, about 3 to 3:50, I've been asked to talk. So about 50 minutes. I think this is a very preliminary introduction to vibration measurement and the sensors and some of the fundamentals that you should know before going to the data acquisition. Next class, we talk about the data acquisition and an introduction to that machine learning in the next topic. With that, we'll close today's talk. Thank you so much. If you have any questions, we can take. Otherwise, goodbye.
Students, you can ask your questions through this today's session. So we will learn more things about the upcoming sessions. We have another 5 sessions in vibration measuring devices and analysis. So you can post your questions in chat box. If possible, you list of questions you can post in our group. I'll share to the sir so that we will get the clear answer in next sessions. Sir, thank you so much, sir, for your the initial startup of the theory of vibration and measuring instruments, where
Thank you,
we have
sir.
started the signal measurements and the measuring units. Thank you, sir. Thank you.
Thank you, sir.
Sir,
Bye, sir.
anyone having questions? Sir, faculty members is having any questions, sir? You can post or you can ask the question with Sumaran, sir.
Any questions from faculty side?
Thank you, Sukumaran sir.
Thank you, sir. Thank you, sir.
Sir, HOD, sir.
Okay, maybe next section maybe train the people. Maybe it will be interactive section.
Yes, sir. Yes, sir. We will
Okay.
connect in mobile also, sir,
Okay,
for
maybe
individual students.
train our student. I have another phone call. Thank you, sir.
Thank you, sir. Thank you.
Sir,
Okay, sir.
everyone-
There, sir. Bye, sir.
Sukumaran, sir, thank you so much, sir. Thank you, sir. We'll meet in another session, sir. Thank you so
Yeah,
much.
we have one international conference with it. So we'll close meeting, and next class we'll meet, sir. Bye, sir.
Sure, sir. Thank you so much, sir. Thank you.